In this video, I want to do an example of finding an equation of the tangent plane. So here's the typical test question. Let capital F of x, y, z equal 4x squared minus y squared plus 3z squared. Find the equation of the plane tangent to the level surface, capital F of x, y, z equals 7 at the point 1, negative 3, 2. So before going over how to solve the problem, let's just make sure we understand what the scenario is and what's going on. So you have this function of 3 variables, right? Now when you have a function of 3 variables, one way I like to think about this is that it's the temperature at the point xyz. So at each point xyz in space, it has a temperature. And let's say that this is the temperature at the point xyz, okay? What does it mean when it says the level surface, capital F xyz equals 7? So in our temperature analogy, okay, this would be all the points in space where the temperature is 7. So, you know, if you look at each xyz and plug them in, you're going to get different temperatures, right? And this is saying, okay, let's look at where all the points are where the temperature is 7. So if you only look at that, okay, so here's our R3, right, x, y, z, and then you look at the points where the temperature is 7. Well, I don't know what that looks like. That's what you get when you set, you know, like maybe this variable is like w. So it's the points in space where when you plug in 4x squared minus y squared plus 3z squared, you get 7. So I don't know what that looks like, but I'm just going to draw, I don't know. It's some surface like this, okay? This is, say, f of x, y, z equals 7. I'm not saying this is the actual shape. I'm just drawing this just to give you an idea of what's going on. And it says, find the equation of the plane tangent to this surface. So this is our surface, our level surface, right? That's the level surface at the point 1, negative 3, 2. Let's check that the point 1, negative 3, 2 is actually on the surface. So when you plug in 1, negative 3, 2, do you actually get that capital F has the value 7? Well, if you plug in 1 for x into, so we're plugging it into this function, right? 4 times 1 squared minus negative 3 squared plus 3 times 2 squared is 4 minus 9 plus 12. And that's going to be negative 5 plus 12, which is in fact 7. Okay, so this point, let's say it's here, it's 1, negative 3, 2. Well, clearly this is not the actual, well actually, yeah, I mean this is not an accurate drawing. I'm just trying to explain the idea. So your point is somewhere on the surface, right? The temperature is 7. And there's a tangent plane like this. And the question is to find the equation of that plane. Now the key fact you need is that the gradient, so remember, what do you need to find an equation of a plane? You need a point on the plane and you need a normal vector to the plane. You need to find the plane, you need to find a vector that's orthogonal to the plane, that's sticking straight out, that's perpendicular to the plane. So it's gonna be like this, right? That's the vector you need to find. That's the normal vector to the plane. And the key fact that you need to know to do this problem is that the gradient vector to this function is orthogonal to this plane. It's orthogonal to the surface, meaning that it's orthogonal to this tangent plane. So This is the gradient of f at the point 1, negative 3, 2. And then once we find that, we find a normal vector, we have a point, and then we can find the equation of the plane using our facts about how to find the equation of a plane. So let's do it. You get the gradient. So the gradient is, okay, f sub x, that's going to be 8x. F sub y is negative 2y. F sub z is 6z, right? Now you plug in the point 1, negative 3, 2, and you're going to get the vector 8. Negative 2 times negative 3 is 6. 6 times 2 is 12. So that's our normal vector to the plane. And once we have a normal vector to the plane and the point, we know this point 1, negative 3, 2 is on the plane. So now we get the equation of the plane. The equation of the tangent plane is 8 times x minus 1 plus 6 times y minus negative 3, that's y plus 3, plus 12 times z minus 2 equals 0. That's just the formula for the equation of a plane where you're given a normal vector and a point. And if you don't know where this formula comes from, then you should go back and review how you find the equation of a plane. So that's the equation of the plane. And depending on your instructor, they may not want you to leave it in this form because it isn't really a standard form. So one way to get into kind of a more standard form is, so a more standard form would be like ax plus by plus cz equals d. So again, in this form, you can distribute across like this. And then you get 8x plus 6y plus 12z, so 8x plus 6y plus 12z, and then you move the constant terms over. So you add 8 and subtract 18 and add 24. That's 32 minus 18 is 14. And by the way, you can even divide both sides by 2 to make this a little more simplified. So you get 4x plus 3y plus 6z equals 7. This is a more standard form of the plane. So it's something that you would want to check with the person teaching the class, whether you should leave the equation of the tangent plane in a certain form. Okay. So that's the answer. But before I stop the video, let's just maybe give some idea of why it's true that the gradient vector is orthogonal, is perpendicular to this level surface. So the point is, if you think about, again, capital F is the temperature, right? If you're on this purple surface, your temperature is always 7. So one of the facts is that the gradient vector always points in the direction of greatest increase. That's a fact about the gradient vector. So why would it be orthogonal to the plane? Well, if you're moving along this tangent plane, right? If you move in the direction of the tangent plane, like this, then you're basically moving along the surface because the tangent plane closely approximates the surface. And if you're moving on the surface, you're not changing the temperature. You're just staying that constant temperature, which is 7. So intuitively, right, if you stay on this plane, at least in the immediate vicinity of the plane, then your temperature is not going to change very much because you're pretty much on the surface where the temperature is 7. So if you want to change the temperature as rapidly as possible, then you should move as not in the same direction of the plane as possible. And that's going to be perpendicular to the plane. So if you move if you want to increase your temperature as much as possible, you would want to be moving perpendicular to the plane. Now there's two perpendicular directions, right? There's that direction and then there's that direction. And then it turns out that the gradient is not just perpendicular to the plane, it actually always points in the direction of greatest increase. That's kind of interesting because, you know, you could be, if you're moving perpendicular, you could be either increasing or decreasing, but it turns out that the gradient points in the direction of greatest increase. I mean, that's not really relevant for this question. You just need a vector that's perpendicular to the plane, and the gradient is going to do that. And that's how to do the problem. And that's basically it for the tangent plane. And then maybe one more thing is that here, the surface, right, is implicitly defined by this equation. Like this is an implicit equation for the surface. This purple surface is described by capital F of x, y, z equals 7. It's not given in the form of the graph of a function. It's not like z equals something, right? It's something in terms of x, y, and z equals a constant. And so again, we would use the gradient for this. There's a different formula you can use when your surface is of the form z equals a function of x and y. Okay, thanks.